And we'll go from the current slide. I guess we'll go from the current slide. There we go. One new announcement that I think I made the one about morning. Couldn't get the old guy up this morning, huh?
He's nervous.
Oh, I see. Okay. Okay. Just a couple of things. I think I announced to you before. Oh. Jake decided to show. Good, good. And here's Chuck. All right. I think I announced to you before about the Alabama A&M University having the North Scholarship Program now. They're just getting it started, and we're a partner with them. Okay? I did make that announcement last time, or not? Yeah, okay. Now, found out a little more information about them because I didn't get the information, I got the email, and I pointed out, y'all got the email too. If you got your awesome email, it went to you as well. But one of the students in my class yesterday checked it and said the things I was saying about summer programs, that's what UAB and Alabama did. A&M doesn't sound like they're doing that. They're just offering scholarships to juniors and seniors who are choosing to go into math and science education. Pretty lucrative scholarships too. I think paying just about everything. So if you're interested, check it out. You got the email. There is a link there. Check it out there. Now, this is JB is here. Okay. All right. This is something that's a little more immediate, as in today and tomorrow. Okay. Wednesday today, the 13th, Friday the 13th is on the Wednesday this week, okay, is from 9:30 until 11:30, so it's right in the middle now, and you're not going to be able to make it, are you? Okay, it's on the Birmingham Campus Academic Building B. Too late, can't make it. But tomorrow, tomorrow it'll be on this campus. It's the College Transfer Fair Days, okay? And that's tomorrow, the 14th, Valentine's Day, by the way, on the Bessemer campus, again, from 9:30 till 11:30. Some of the schools that are scheduled to attend: AUM, Troy, Mississippi State, University of South Alabama, University of Alabama, University of Alabama College of Continuing Studies, Montevallo, Athens State, Alabama State, UAB School of Health Professions, Faulkner University, Auburn University School of Forestry and Wildlife Sciences, University of North Alabama, Alabama A&M, University of West Georgia, Auburn University, Jacksonville State University, Stillman College, University of Alabama is here again, okay, UAB, UAH, University of West Alabama, Talladega College, that's going to show up again. Okay, let me pick up over here. Did I say North Alabama? Samford University, Fisk University, Mississippi College, Tennessee State University, Faulkner University, Southeastern Bible College, Talladega College, Georgia Southwestern State University, wow, okay, and William Carey University. Whoa, okay. That's quite a list. And they should be here tomorrow. Now, where they are on this campus tomorrow is in the faculty cafeteria. It's also called the faculty and staff dining room. Do any of you know where the cafeteria is who are interested in attending this? Or any of you not know where the cafeteria is who are interested in attending this? Nobody is interested in attending this, okay? The faculty staff dining room is just this side of the cafeteria, the student cafeteria. So find the cafeteria and then ask someone, where's the faculty staff dining room? It's just, you can enter it from the hallway, 2 doors from the hallway, or you can enter it from the cafeteria. So find the cafeteria and you'll be right there. 9:30 to 11:30 tomorrow. Bunches of colleges will be here. They're at Birmingham campus right now, but they will be there only till 11:30, and see, this class goes until 11:40, so it's going to be hard for you to make it, and don't you leave. No, I'm sorry. Okay. All right. I think I marked everyone here who came in. Any questions? Anything we've covered so far? Anything about the Alabama A&M, the college fair transfer dates, any of those things? All right. We did this slide no, we didn't. Not quite ready for this slide. Okay, here. We did example 8 last time, and we finished it, but there was no slide for example 9, so that's where we are today. If I can get the pen to operate. There we go. It's not communicating well. There we go. Yeah, it's been a long time since the pen has gotten out of sync, and it looks like it's almost trying to do that today, but it's better now. All right. If no questions on anything we've done so far, and Frederick decided to show, that's good. Okay. All right. Good deal. All right. Differentiate both forms of this function. Okay? And Frank's here. Gonna make a class after all, I think. Okay. Y is equal to 1 minus cosine x divided by sine x. Okay? It says to differentiate that form as well as, and I want you to confirm with me, is this legitimate? Cosecant x minus cotangent x. Could those two possibly be the same function? Say again? I turned on the wrong light today, didn't I? It's a little dimmer than usual. Okay. Are those the same functions? All you have to do is split the numerators over the same denominator, right? 1 over sine is? Oh, it's been a long time. All right, here's Josh. Okay. Anyone else coming in since I called it? 1 over sine is? Cosecant. And cosine over sine is? Cotangent. So that's minus, cosecant minus cotangent. Yes. Now they want us to integrate each of them according to how they look. So what would you need to do for the first one here? To take the derivative, I said integrate, didn't I? Differentiate, I'm in the wrong course. Differentiate that. How would you do it? What rule would you use? All right.
Quotient rule.
Quotient rule, absolutely. Let me get Ayana here. Couldn't see where you sat. And even, you know you're in here. No? Cedric. All right. Slowly filling up here. I think the only one we're missing is Taylor, right? Way to go, team. There's a couple who's never been here, so I'm not counting them anymore. But of our regulars, Taylor's the only one missing. Glad y'all are here. Okay, quotient rule is what you said. And how does the quotient rule go?
Why can't you just take the derivative of cosecant x minus cotangent x?
Okay, they want us to do them both, just to see if the derivatives work both ways. Okay. Dumb, but yes, okay. So how does quotient rule go? And to give you practice on the quotient rule, right? How does it go? sine x, that's low, yes, times sine x. You're right. Okay, that's d high minus, that's high, 1 minus cosine x times cosine x. Okay, all over sine squared x. Okay, what a mess. Okay, let's see what we got here. Up here, first one term is sine squared x, right? Minus cosine x, right? Plus cosine squared x, right? All over sine squared x. Agreed? I should be letting you do the talking. Got it? Any part you don't see? Sorry, I should have let you do it. Okay? What do you notice about that numerator? Say again? What about it? You want to do what? You can't factor it out because it's not common to that term. There's 3 terms here, and it's not common to that term either, okay? But what can you do with it? Now, there's a few things you could. You could put this over this and make it 1 minus this minus that, or plus that. But, and that may be a good thing to do, but what do you notice here? Sine squared x plus cosine squared x is 1, okay? So that'll be 1 minus cosine x over sine squared x, okay? Well, let's split that up. What's 1 over sine squared x? And look at this, folks. Ding, ding, ding. Perfect attendance. All right. Taylor, put us over the top. Way to go. All right. 1 over sine squared is? Cosecant squared x minus, let's write that as cosine x over sine x times 1 over sine x. Do you agree with that statement? Cosine x over sine squared x, you can factor this as cosine x times 1, put each one of them over a sine x, and that'll be it, right? This will be cosine x over sine squared x, right? Yay or nay?
Yay.
All right, yay. All right, good. All right. Now, what is cosine over sine? Cotangent x, so that's cosecant squared x minus cotangent x, and what is 1 over sine x? Help me, somebody. 1 over sine x? Cosecant x. All right. All right, that was the taking the derivative of the left-hand side, or this one, okay? Let's take the derivative of this. Y prime of this, what's the derivative of cosecant x? Ooh. If you need to refresh, oh, there it is. Derivative of cosecant x is? Negative cosecant x, cotangent x, right? So that would be minus cosecant x, cotangent x. And then, what is the derivative of negative cotangent x? Plus cotangent, no, Cosecant squared x. Okay, I thought you said tangent. Said that ain't right. Okay. Plus cosecant squared x, which is exactly what we got here, only we have the minus term second here, and just reverse the terms and you got it. Indeed the same. And this is one time when I say, okay, let's fiddle with the cofunctions, rather than doing sines and cosines. The derivative's a lot harder to get to, real easy to get to there. Okay? Got it? That's all we wanted you to do. Show that the derivatives were indeed the same. Any questions? All right. If none, then this is where we would have been, starting today. After that, this was the next slide. The summary below shows that much of the work in obtaining a simplified form of the derivative occurs after differentiating. The calculus is the easy part. It's the math that's the hard part, the algebra, the fixing it and making it look pretty. Note that the two characteristics of a simplified form are the absence of negative exponents and the combining of like terms. Okay? Now, example 1, which we did a while back, this was what we got after differentiating. That part was easy. If my memory's right, this was the first function, this was the second function, it was a product function. We took a derivative, first times derivative of the second plus the second times derivative of the first. Okay? That was the easy part, okay? Just the product rule. But then you have to combine or distribute, FOIL, combine like terms, simplify, and that's what you get. We got it already. You don't have to go back and do it again. Example 3, and again, they put these vertical lines in weird places, and I don't know why it's not in the book, but it's typesetter. Okay. This must have been, I don't remember. It looks like a product rule as well. It was 2x times cosine x minus or plus 2 sine x, or something like that. And anyway, here was the derivative, pretty easy, but then you have to combine all the like terms, and here you had a plus cosine 2 cosine x and minus 2 cosine x. It left you with just that. Again, that was pretty simple. Okay, this must have been a quotient rule. It looks and smells like a quotient rule. You got something times something minus something times something over something squared. So that's a quotient rule. Low d high. And that was pretty easy to do. Once you get that down. But then you had to multiply here, distribute here, distribute there, combine like terms and stuff, and you came up with a simpler representation. All right, this must have been another quotient rule. It sure looks like it. And again, distribute, FOIL, whatever at least, the denominator doesn't change, combine like terms. And then the one we just did, I think, that's the one we just did. It came out. The quotient rule wasn't bad, but when you combine like terms, you wound up with a sine squared here, a plus cosine squared there. That went to 1, and then just a plus cosine. No, minus cosine here. Minus 1 times cosine over sine squared. Okay. Not a particularly instructive table in my mind, but I guess he's just showing don't stop believing. Don't stop just at the taking the derivatives, because you usually can simplify things greatly, and that may take longer than taking the derivative did. The calculus part's easy, isn't it? It's all the other stuff. All right, higher order derivatives. Just as you can obtain a velocity function by differentiating a position function, you physics students, you can obtain an acceleration function by differentiating a velocity function, because acceleration is the time rate of change of your velocity. What do you do if you want to change your velocity on the highway? You accelerate, yeah. So it's the time rate of change of acceleration, is the time rate of change of velocity. Another way of looking at this, you can obtain an acceleration function by differentiating the position function twice. Because you differentiate it once to get the velocity, then differentiate a second time to get the acceleration. So, fairly simply put, if this is your position function, s of t, position is a function of time, and that's usually measured in a length measurement, time is in seconds, but it's a function of time, then derivative of this per unit time, that would be distance per time, that's the velocity, that's your s prime, and then to differentiate this to get your acceleration, that's taking a second derivative of your position function. That gives you your acceleration. Not too big a surprise, is it? Okay. So, the function a of t is then the second derivative of s of t and is denoted by s double prime. I think that may be the first time we've hit double primes, was it? Okay, I'm teaching so many different classes. We're using them all the time in other classes, but yeah, that's the first time we hit it in this one. Okay. The second derivative is an example of a higher order derivative. You can define derivatives for any positive integer order. For example, the third derivative is the derivative of the second derivative, and on and on and on. Now, polynomial functions, you can only take as many derivatives as you have degree of the polynomial. Okay, after that, they start going to zero. Okay, you can still take them, but derivative is zero, a constant is zero, and derivative of zero is zero, and after a while, nothing new shows up. But other functions, you can just keep taking and keep taking and keep taking. All right, so higher order derivatives are denoted as follows. Your first derivative is y prime, or f prime of x, or dy dx, or dy dx, d by dx of f of x, or this other notation, derivative. This is derivative operator operating on y, or on f of x. That is derivative operator with respect to x. That means d by whatever is here, dy by dx. This thing stands for d by dx. Okay? This operator here, d of x, is d by dx. And then you just put the y here, and that's exactly this form. Put the f of x there, you got exactly that form. Okay. Now, second derivative then would be y double prime, f double prime, the 2y dx squared. Now, that's a little weird, isn't it? Here's where it comes from. You're taking d by dx of dy dx. So, d by dx of this, you have two d's next to each other, so you square that of y, and then you have two dx's by each other, and that's why you put it like that. That doesn't mean you're squaring your, this is just a notation, okay? And that's the same as here, and this would be the same here. d2, d squared of x. This means this notation is this thing right here. Everything except the y does what d squared x sub x. The third derivative, y triple prime, f triple prime, d3y dx cubed, d3y, this is hard to say, d3 third dx cubed of f of x, or your third derivative operator of y. Just this thing here is that thing there. I would have put those next to each other. Now, notice I use prime for first, second, and third. After there, you start running into so many primes, you get like, hey, is that 4 or 5 primes there? By ink sort of smeared, it really gets hard to see. Okay? Now, I think, and Bill, correct me if this, and maybe Chuck too, it seems like we used to use Roman numerals after the primes. Did y'all ever, were you familiar with that? Okay, I may be thinking of something else. But nowadays, this is what they do. They put it in parentheses. Why don't they just put a 4 there? Why parentheses? look like raising it to a power. You can't do that. So a function representation, okay, with a number greater than 3 in parentheses means fourth derivative of y, fourth derivative of f of x, okay? Here it's pretty clear, d4y dx to the fourth, or d4y dx by dx of f of x of d. d fourth by dx to fourth of f of x, and then your d sub x operator to the fourth of y. This thing right here is that thing right there. Okay. By the way, people at home can't, well, no one's at home. I mean, y'all are all here. Okay, good. They can't see this thing here, you know, when I point to it. I should be doing it on the screen. I hate sitting all the time. So if it's anything greater than third, the nth, that means the nth derivative of y, nth derivative of f of x, the dn y over dx to the n, dn by dx to the n of f of x, or d sub x to the nth of y. Those fill in the n for any derivative you want to have. Okay? Let's see if they do. Yeah, they do example 10. Because the moon has no atmosphere, a falling object on the moon encounters absolutely no air resistance, and in 1971, astronaut David Scott demonstrated that a feather and a hammer fall at the same rate on the moon. You probably have heard, who was it? I guess Galileo first hypothesized that, but the difference is on Earth, the feather has far less weight, far less mass, and bigger surface area per unit mass, so therefore it encounters a lot of air resistance. So you drop a hammer and a feather, and the hammer is going right down, the feather just wobbles, okay? Finally gets there after a while, as long as it's not too much wind, okay? But on the moon, and there's actually pictures of them doing this, hammer in this hand, feather in this hand, drop it at the same time, okay? All that depends on, in the absence of air resistance, everything falls at the same rate. Same rate as on Earth? No, because the moon has a lot less of a gravity function than the Earth does. So the position function for each of the following objects is S of t is equal to negative 0.8 t squared plus 2. Now, without any description here, I'm going to try to tell you what that's meaning. I'm assuming the acceleration due to gravity on the moon is about 0.81. That's, no, twice that, 1.62, okay? Yes, that's right. And this will be in meters per second squared, okay? So that means why the plus 2 here? He's holding 2 meters above the ground, earth ground, okay? That's where the plus 2 comes from. If you remember our function, I think we did this in here, didn't we? 1/2 AT squared or GT squared plus V naught T plus S naught, S sub 0. And this is what it would be on the moon. Where S is, height of the, in meters, so that means he has to be holding up like this, 2 meters above the ground. And T is the time in seconds, and what is the ratio of Earth's gravitational force to that of the moon's. We say to say gravitational acceleration to that of the moon's. That would be a lot better. Okay? Well, what's the answer to that one? What's the Earth's gravitational acceleration? Anyone know or remember? 9.8 meters per second squared. You got to get in the same units. And this one I said, remember, you just double this because this is 1/2 that. So that'd be 1.62 meters per second squared. And someone just do a quick ratio there and see what you get. 9.8 divided by 1.62. Anybody? I don't want to do it in my head. I can't. I don't want to. It's too early in the morning. Say again? 5.85 you said? 5.555. Okay. I was thinking it was closer to 6 than that, but that sounds reasonable to me. They say about 6.0. Say again? Oh, okay. 6.05. Or they say about 6.0. That's all I've always did. It's about a 6 what the Earth's gravitational acceleration. Oh, and there is the picture, isn't it? Except I don't see either the hammer or the feather, but maybe you can see it. I've seen a better one than that. All right. And they said about 6.0. Not a lot to do with second derivatives, but I guess it's there. Exercise set 2.3. Any of the odds 5 through 9, they're all at Calc Chat. 5's at Calc View. Any of the odds 11 through 15, they're all at Calc Chat. 11's at Calc View. Any of the odds 17 to 21, they're all at Calc Chat. 21's at Calc View. Any of the odds 23 to 27, they're all at Calc Chat. The 23's at Calc View. Any of the odds 29 to 39, they're all at Calc Chat. Any of the odds 41 to 55, they're all at Calc Chat. Any of the odds 57, no, just do 57. Now it says using technology, see if you could do it without it, but if you got it, use it, whatever. Okay, then either 59 or 61, they should both be at Calc Chat. Any of the odds 63 to 67, they should be at Calc Chat. 69 or 71 should both be at Calc Chat. Do either 73 or 75, they're both at Calc Chat. 75's at Calc View. Do 77. Okay, do 79. They should both be at Calc Chat. Do 81. It should be at Calc Chat. Then I would say do your choice of any of the odds 83 through 89. They should all be at Calc Chat. Then any of the odds 91 to 99, they finally have you do some second derivatives, so please do some of those. They didn't give any on the examples. They should all be at Calc Chat. 91's at Calc View. And then they say do thirds and eighths derivatives of 101 and 103. They're both at Calc Chat. 101's at Calc View. Do either 105 or 107. They should both be at Calc Chat. You can explore doing 109 if you'd like, 111 if you'd like, and 113 if you'd like. Whoa, here's some more. Any of the odds 115 through 119, they should all be at Calc Chat. They're looking for patterns here. 121, that should be at Calc Chat. I'm sorry, yeah. And 123 is a pattern. And 125 is a pattern. So I'd say do at least one of those. Now, differential equations, that seems like another course, but you can do either 127 or 129. They should both be at Calc Chat. There's a few true false, any of the odds 131 to 135. They should be at Calc Chat. And then if you're really anxious, you've been missing proofs, there is a proof at 137. All right. Any questions on that? Sorry, I've got, like I said, I had a sneezing fit this morning, and that's loosened everything up. So I'm having trouble breathing. Sorry about that. All right. Oh, here was example 10. I forgot to show it. I went from the equation, they did it more calculus-wise. There's your position function, so take a derivative of that, and you get the velocity function. 2 times negative bang, that disappears, so that's times t. Then take the second derivative, and that gives you the acceleration. That then, which I got from just multiplying the thing by 2 because that was 1/2 t gt squared. But it's got the same thing. That's your acceleration, and that's what you divide by, or divide into 9.8. And that gave you, so this did have some calculus in it. I just failed to see the connection. Okay. Sorry about that. Okay, any questions? That's 2.3. Let's move on to 2.4 if I can get this to discard. Okay. 2.4. Do y'all remember back when you were doing pre-calculus algebra and they introduced something to you called composite functions? That's it. And you said, you thought to yourself, oh, they're just doing this to give me something else to have to think through, you know, made up some problem here, made up a, no, not at all, okay? Chapter 2 is differentiation, 2.4 is the chain rule, and this involves taking derivatives of composite functions, okay? So there was a reason for them to introduce that to you rather than just giving you something else to have to learn, right? So here's the objectives here. We'll find the derivative of a composite function using the chain rule. We'll find the derivative of a function using the general power rule. I thought we had already had that, but we'll see that. Simplify the derivative of a function using algebra. We've been doing that. And we'll find the derivative of a trigonometric function also using the chain rule. Okay? This is as opposed to the chain gang. Okay, so let's do the chain rule. We have yet to discuss one of the most powerful differentiation rules, and everybody's favorite, by the way, the chain rule. Okay, I have a guy in my Cal 3 class right now. He said, I always never did get the chain rule. You know, fortunately I wasn't an instructor earlier, but hope he's getting it now. This rule deals with the composite functions and adds a surprising versatility to the rules discussed in the 2 previous sections. Oh, I can't wait to be surprised. Okay. For example, compare the functions shown below. Those on the left can be differentiated without the chain rule. Those on the right, best differentiated with it. Yeah, we can take the derivative of that, right? Pretty easy. 2x. This is, okay, not so easy, okay? Even if you wrote this as x squared plus 1 to the 1/2 power, that would be a good first step. Still, what do you do from there? You can do this one, y equals sine x, this derivative, yep, cosine x. Sine of 6x, oops, okay. Cosine 6x is part of it, but that's not all of it, okay. 3x plus 2, that's really easy, okay. 3x plus 2 to the 5th power. I can do that. I can take 3x plus 2 and multiply it by 3x plus 2, multiply it by 3x plus 2, multiply it by 3x plus 2, multiply it by 3x 2. I think I got them all. That would be a lot of fun, and then I know how to take the derivative of a polynomial function. Piece of cake, right? Here's our surprise versatility, okay? Make it so much easier when you do the chain rule. That one, yeah, we can do. What would that be? Derivative. One plus, what'd you say? You may have said it right. Secant squared, excellent. Well, how about that one? X plus the tangent of x squared. Now that's not tangent squared x. That would also be a little bit of an issue, but not bad. But tangent of x squared, no way to do it without the chain rule. And we don't even know what the chain rule is. Basically, the chain rule states that if y changes dy du times as fast as u, okay, in other words, time rate of change of y with respect to u, that's what it's saying here. Dy du is the change of y for the unit change of u. That's what it says. Changes dy du times as fast as u. I don't think I would have ever thought of expressing it that way, but that's what it's true. And u changes du dx times as fast as x, then y changes dy du times du dx times as fast as y. Yeah, okay. I think I understand that, sort of. Okay. Now, remember these are operators. They don't mean division. But look at this. If you think of this as that du's in the denominator sort of, and that one's in the numerator sort of, and you sort of cancel them out, you get dy dx, don't you? And that really is a pretty good way to think of it. Okay? Don't ever tell if you're a mathematician that way. Okay. They go a little nuts with that. Okay. So here's example 1. Let's see if this makes any sense. Actually, all these let's investigate and see type things are more confusing to me than just doing the chain rule. Let's tell us what the chain rule is to do it. Set of gears is constructed as shown in this figure, okay, such that the second and the third gears are on the same axis. Okay, this is gear 2 and there's gear 3. Here's gear 1 over here. You turn a crank, okay, at a certain rate. It turns gear 2. Anyone going to guess whether this turns faster or that turns faster? Say again?
The small always turns faster.
What's that?
Small always turns
Yes, it turns. You got to go one time around here, only gets you a few teeth on that. So yeah, it's small always is faster. But this is on the same axle of a small one here, and I didn't count the teeth, but it looks about the same. And then this is going more slowly, but this is going slowly too, and this turns in gear 4 on a third axle. Okay. Yeah, okay. And this is a 1 to 3 ratio, a 3 to 1 ratio, and a 1 to 2 ratio. Okay. So yeah, these two are the same. Okay, I thought they looked like they were. Okay, and again, the example I think is more complicated than just doing the chain rule, but let's see. As the first axle revolves, it drives the second axle, which in turn drives the third axle because it's on the same, the third gear, which is on the same axle, and that drives the third axle. Okay. Let Y, U, and X represent the numbers of revolutions per minute. Okay. Numbers of revolutions per minute of the first, second, and third axles. So Y is the revolutions per minute of the first axle, U is the revolutions per minute of the second axle, and X is the number of revolutions per minute of the third axle. Okay. Find dy du. Okay. And they give you a ratio here of radii, which is also a ratio of diameters. And believe it or not, that will also be a ratio of teeth. The teeth are the same size. Okay. So, du dy, what would that be? Any guesses? The ratio of the number of revolutions per minute of the first axle to the number of revolutions per minute of the second axle. Make a guess. So the second axle is going to be slower. And they suggest a ratio here of 1 to 3. What might it be? 1 over 3. That's what would be my guess too. Okay? Now, the ratio of du to dx, the number of revolutions of the second axle to the number of revolutions of the third axle, gear 4. What would that ratio be?
1 over 2.
1 over 2. Okay, perfect. And then guess what dy dx would be? If this is 1 over 3 times 1 over 2, what do you reckon that would be?
1 over 6.
Yeah, that's a guess. Let's see if that's how it comes out. Okay? because the circumference of the second gear is 3 times that of the first. I came close to saying that, and I didn't. Because the ratio is 3 times, that's the radii is 3 times, that means the diameter is 3 times, and diameter is related to the circumference by what? Constant. Pi. Exactly. So that is a linear relationship, so the circumference will also be a ratio of 1 to 3. And the circumference is the number of teeth. It's related to the number of teeth as long as the teeth are the same size. Otherwise, the gears get messed up. Okay, so because the ratio of the circumference of the second gear is 3 times that of the first axle must make 3 revolutions to turn the second axle once. Okay? Similarly, the second axle must make 2 revolutions to turn the third axle once. Okay? So when the first one turns 1 time, the second one's only turned 1/3 of a revolution. And when it turns 1/3 of a revolution, the other one turns half that much, and half of 1/3 is a 6. So yes. I disagree with that. Say dy du is equal to 3. Now, if I understood their problem, y is the number of revolutions per minute of the first axle. I'm having trouble with this. Let's see where they go with it. dy du is 3 and du dx is 2. Combining those two results, the first axle must make 6 revolutions. Okay. I think they stated this wrong. Okay. I agree what they're saying here must make that number of revolutions. So let's go on and read the problem. I don't agree with their thing. Combining the first axle must make 6 revolutions to turn the third axle once. Yeah, and that's exactly what we said. But they say, okay. What they're saying is revolutions, not revolutions per minute. If you went back to the original problem here, and maybe I'm nuts, but I'm doing what they say. This number of revolutions, not number of revolutions per minute, is what? Okay. Yeah, if here you said, let y represent the number of revolutions on a given turn, u be, on the first, second, third, revolutions, not revolutions per minute. I don't think that could be true. Because like Bill said, the bigger axle is going to turn more slowly than the little one. The little one has to turn faster. So I think the way we did it was right. They're saying the same thing, but they're saying it's 6 revolutions. Y is making 6 revolutions for every revolution of X. Okay. Which is, if you count it revolutions, that's it. Revolutions per minute, not. Okay. I believe that's the case. But again, I said the rate of change of first axle with respect to the third oh wait. Okay. As I said, this problem is more complicated than the chain rule, okay, on how they worded it, okay. They may be right on this because the number of revolutions of the first has to be faster than the number of the revolutions of the third. That's right. So the 6 is right. The rate of change part was the revolutions per minute. The way they stated it just seems like it got it wrong. But I think they're right. Okay. Here's the chain rule. Get away from these introductory problems, okay? the chain rule. If y is f of u, where u is also a differentiable function. Not just the y, not just the f, u is also a function, okay? I'm sorry, let me say this again. If y is equal to f of u is a differentiable function, y is, f is, okay, of u. But u is also a differentiable function of x. U is g of x, okay? Then y is f of u, but u is g of x, so y is f of g of x, which is the definition for a composite function, okay? And if you're taking the derivative of this, you take the derivative first with respect to u. Well, it doesn't matter which order you do. Y with respect to u, and then u with respect to x. And again, the visual that'll help here, it looks like those are canceling out, and that gives you the same thing. That's just a visual, okay? That's not, you don't cancel out parts of an operator, but it really does work out that way. So another way to say it is f prime with respect to g plus times g prime, okay? Just like we did before, taking derivatives, multiplying them by each other, okay? dy dx is dy dg, basically is what you're saying here, then times dg dx, okay? And again, the way you express it doesn't matter as much as how you do it, but that is the proper expression of it. So when applying the chain rule, it's helpful to think of a composite function, f composed with g. Remember that little notation. Always seemed like it made things foggy to me, but that wasn't what it was there for. Having two parts, inner part and the outer part. And this is how I think of it. Y is equal to f of g of x. F is the outer function, g is the inner function. Okay? U is the inner function. Okay, if you express it as f of u. The derivative of y with respect to u, take the derivative of that outer function at g, or at u, and then take the derivative of the u with respect to x, or g with respect to x. Okay? And it's a product of those two. Again, the wording, the representation of it, I feel like it becomes clearer when you actually do it. Okay. Now, if that's a composite function, what are your two functions there? What's your inner function? Let's start with that. The simplest representation.
X plus 1.
X plus 1. What's your outer function? 1 over x, okay? So the u is x plus 1, that's your g of x, and your outer function is 1 over u. The u is g of x, and then f of u would be f of, and u is x plus 1, so it would be 1 over x plus 1. Okay. That's just going over composite functions. Now, that's all we're doing right now. We're not taking derivatives yet, okay? Sort of thank you very much here, okay? What would that one be? What's the inner function? 2x. That would be your u, and your outer function is sine of u. Sine of u there. If you're naming this u, then make that u there, okay? Back when we were doing it in pre-calculus algebra, they liked using the same variable in both places, which made it fairly, to me, not that rigorous. Okay. How about this? What's your inner function there? Got me. Pretty simple, right? 3x squared minus x plus 1. That's your u, and what would be your outer function? Square root of u, or u to the 1/2 is how I like to do it. But it is square root of u. Okay? How about this one? What's the inner function? Tangent x. And the outer function would be? This squaring function, yeah, that's u squared. Okay, u squared. You square what that u is, which is the tangent. I think that's all, yeah. So, all that, and they haven't given us an example. Well, we had that first really important example. Okay, they're skipping examples 2 and 3, which to me are far better examples to do. So let's do example 2. I think we got room here.
They did do example 2.
What's that?
That was example 2.
Oh, it was example 2, so they're skipping example 3. Sorry. Wasn't much of an example. Okay, let's do example 3. Let's actually do one, okay? Find dy dx for this function. We're looking for dy dx for y is equal to x squared plus 1 cubed. Okay? What would be dy dx?
3 times x squared plus 1.
Perfect. 3 times x squared plus 1 squared. Just treat this as some new variable. They like to call it u. And what would be the derivative of u cubed would be 3u squared, right? Okay? Now comes the chain rule part. Times the derivative of the inside, 2x. Okay? Now you got a little simplification to do, and what would that be? 6x times x squared plus 1 squared. Do you have to square that? Not if you can help it, okay? You know, if there's no reason for you to leave it that way, it's as simple as you can do it, okay? When would you ever want to square it? If you really hated the product rule and had to do a second derivative of it, yeah, then you could square it, but the product rule is generally a little faster than having to square things, but squaring's not bad either, okay? But leave it like that. Let's see what they did. That's exactly how they left it. Good for them. Does that make sense? Take the derivative of the outer part, 3 blah, 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 with this in there. The g of x, the u is in there, okay? And then take the derivative of the inner part. And that's just 2x. And it's multiplied. And then simplify. Any questions? Does it make sense? All right. Bless you. All right. Now let's go to the general power rule. Okay? Here's a function. Basically, we just did it. Okay? The function y is equal to u of x raised to the nth power. That's exactly what we just did, wasn't it? We had x squared plus 1 was our u of x, and 3 was our n. Okay, we just did it. One of the most common types of composite functions. We just did one of them. The rule for differentiating such a function is called the general power rule. He was a great general, by the way. Okay, and it's a special case of the chain rule. We just did it as the chain rule. Okay, and here's how they express it. If y is equal to u to the x raised to the nth power, where u is a differentiable function of x and n is any rational number, not just integers, not just positive integers, any rational number, positive, negative, fraction, decimal, whatever, okay? So, what would the dy dx in? You tell me. What would it be? Take the derivative of this thing. Again, people at home can't see what this thing is, but I'm glad you're all here. What would it be? N times u of x to the n minus 1 times u prime. Exactly. du dx. Perfect, perfect, perfect. You see how it works? Just like we did the last one. Or equivalently, saying the same thing, the only thing they've done is take out the brackets and the x and change that to a different form. du dx, or d by dx of u to the n, well, they changed the side too, is n times u to the n minus 1 times derivative of u. Remember, u has to be a differentiable function. If it's not, don't use it, okay? You can't use the general power rule, or even the chain rule, okay? Does that make sense? Just what we did earlier. All right, here's example 4. I think they aren't skipping any here. And let's see, I even brought my watch today, didn't I? Yes. Wonders never cease. Okay. We go to 11:40, right? Yeah, okay. Have to stop and think what day it is, what class it is, how long it is, all that kind of stuff. I was just doing schedules for summer, and of course all the times are different in summer. So, all right, find the derivative of f of x equal 3x minus 2x squared raised to the third power. So let's just shorten this by f prime of x. What would that be? Anybody? Where will we start? 3 times 3x minus 2x squared to the second power times 3 minus 4x. Is that what you said? Excellent. Okay. Now, I sure hope they don't want us to clear this, but we can combine these two parts. 9 minus 12x times 3x minus 2x squared squared. And I don't even see why that is a big improvement. So I think either of those two answers would be fine. I see no advantage in trying to simplify any further. Please don't either. Let's see what they do. No, they left it just in that first form right here. Don't even mess with that. Okay. But it's hard to tell with the book. Sometimes they'll carry it another step or two, and sometimes they don't. Okay. Does that make sense? All right. Let's see how they did it. So we'll see what they did. All right. First, let u be. Did y'all do that? You really did without even thinking about it, but you did, okay? But it's not necessary. But if it helps you see it, do it, okay? Do whatever it takes so you understand what's going on. So if you want to do that, certainly do that. Then f of x, if u is the inner part, 3x minus 2x squared, then f of x would be 3x minus 2x squared to the third power would be u to the third power. And then by the general power rule, the 3 is your n times 3x minus 2x squared to the n minus 1. That would be to the second power. Then take a derivative of u, which you have up there, and that was 3. Derivative of 3x minus 2. I'm glad they took so many steps. It's really clear. Makes it clearer, doesn't it? Okay. 3 times 3x minus 2x squared times the derivative of that would be 3 minus 4x. Y'all did it right off the top without going through all the steps. If going through all the steps makes it easier for you to see and understand, do all the steps it takes. Just do them right, okay? That's the only requirement. And that's how they left it without any further supposed simplification. All right. Any questions on that? Does it make sense? Now they have a couple more examples they didn't show on the slide set, so let's do those. Example 5. Find all the points on the graph of f of x. Wait a minute. We were just doing chain rule. Why are they doing this? The cube root of x squared minus 1 squared. Okay? In other words, are you kidding me? Okay? Find all the points on the graph for which f prime of x, I hope it is, yeah, does not exist. Whoa, boy. Now, what you reckon we're going to do?
Chain rule.
Second?
Using chain rule.
I would guess we probably are going to wind up using a chain rule. And you like taking derivatives of radicals? No, we don't, do we? What do we do?
Make it x squared minus 1 and put in parentheses to the 2 over 3.
Hey, very good. Do you hear what he just said? This is to take this out of the picture. We put this to this thing here to the 1/3 power, okay? And then you got something to a power, second power raised to the 1/3 power, that would be x squared minus 1 to the 2/3 power. Now we can use, what do we call that? There it is, general powers rule, okay? Now, because we have a function that's differentiable raised to some power. And the power can be any rational power. This is indeed a rational power. Okay, not nearly as nice as an integer, but it's still fine. So what does this tell you f prime is? But wait. Why am I taking a derivative anyway? Oh, we need to see where that derivative doesn't exist. Well, I guess the only way we can do that is see what the derivative is. So let's take a derivative. F prime of x would then be what? 2/3 x squared minus 1 to the what? Negative 1/3, is that what I heard? Excellent. And then that's times what? Can't forget the chain rule. What's that? 2x. All right. Now, going to rewrite this somewhat slightly, okay? Just because that's sort of messy looking. To take a derivative, get it in exponential notation. You don't want the radicals in there. But then to figure out what's going on, it may be helpful to go back and put it in radical notation. So what would this be then? 4x is in the numerator. 3 times the cube root of x squared minus 1. Okay. Now we want where this thing doesn't exist. Now there's a couple things that can make an expression not exist. Name a few of those for me. Second? 0 in the denominator. In other words, the denominator becoming 0. Can this denominator ever be 0? Where? Okay, it's wherever this thing is 0, right? And wherever that thing is 0 is, you've already done the steps, x squared minus 1, here's how I like to say it, cannot equal 0. Because 3 can't be 0, and the cube root of 0 is 0, so it's where that's not equal to 0. And then how would you, there, and you already did it in your head, I think, but or you looked in the book or on your screen or whatever, I don't know. But where is that equal to 0? X plus or minus 1. Okay? If you need to, go on and factor this, it's x plus 1 times x minus 1, and that product can't be equal to 0. That means neither one of those. That means x plus 1 is not equal to 0. Not just or, and x minus 1 is not equal to be 0. So this means x cannot equal negative 1, and x cannot equal positive 1. Okay? When you add or subtract from both sides. So those are the two places where this derivative does not exist. Okay? Does that make sense? Now, thank them very much. They graphed it for you so you can see sort of what it looks like. If I can hold the book here, that's what it looks like. Okay? It comes down like this, and where the first derivative doesn't exist will be here and here. You see, it's a first derivative is going to negative infinity here, suddenly flips to positive infinity here, then turns around and is going to negative infinity there, and then flips and go to positive infinity there. Nope, doesn't exist at plus or minus 1. Does that make sense? All right. What are the other two places that you have to, a function could not exist? You can't have 0 in the denominator. Got that one. What two others do we usually concern ourselves with?
You can't take the square root of a negative number.
A little louder.
You can't take the square root of a negative number.
You can't take the square root or any even root of a negative number. You can take the cube root of a negative number. That's why that wasn't an issue here. That's the cube root. If this had been a square root, then we have more things to worry about. Okay? Because you can't take the square root of a negative number, then you'd have to exclude all the values that would make that negative. But you can take the cube root of a negative number. So any even root, you can't take the what's inside the house can't be negative. Okay? It has to be greater than or equal to 0. Then it won't be an inequality, it'll be a greater than or equal to. One other thing. Function we haven't dealt with yet in this course, I don't recall that we have. Anyone know what it might be? It's associated with the exponential function, but it's not the exponential function. It's the inverse function of exponential. Logarithm. Okay? Now, if you picture what an exponential function looks like, it never is negative. Okay? It's approaching 0 as you go to negative infinity, and then gets very, very high. But no asymptote here, it just keeps going up. Okay? But then you take that and reflect it across the identity function, and you have this as your log function, which cannot be negative and cannot even be 0. That's its vertical asymptote. So a log function can't be either negative or 0. So you have more things here to do there. This didn't deal with logs, so we don't have to worry about that. Those are the things you keep in mind when you're trying to find out where something doesn't exist. Can't have 0 in the denominator, can't have negative numbers in square roots, and you can't have either a 0 or a negative number in a logarithm. Okay, let's do example 6. These were so much fun. Really, chain rule is fun. All right. Differentiate this function. G of t is equal to negative 7 over 2t minus 3 squared. Now, before we talked about chain rule, what would we have had to have done with this? Our favorite rule of all time. The quotient rule, okay? But, well, not really. We could have used the power rule. How would we have rewritten this to use a power rule? Negative 7 times 2t minus 3 to the negative 2. Except we couldn't have done that because we didn't know the chain rule then. So that would have been a nice way to do it, but we didn't have the chain rule. Now that we do have the chain rule and the general power rule, okay, we can do it. So what would that be? Take the derivative of that one. Frankly, I think you'll like it better than quotient rule, but maybe not. Maybe you love quotient rules, okay? What would that be? Take the derivative of this using the general power rule. Anybody? How does it start? 14 times 2t minus 3 to the negative 3, excellent, times 2. Okay, this is pretty easy. That would then be in the numerator 28, because this and this are both in numerators, over 2t minus 3 cubed. Okay. Now, they didn't ask us where this won't be defined, so we're not worried about that. But it's the same place this one wasn't defined, right? What can t never be? Second?
Plus 3.
Okay.
Plus 3.
Well, 3 halves.
Oh,
Yeah, yeah, 3 halves. T cannot equal 3 halves. That's the same thing here. I mean, it stays in the denominator, so it still can't be 3 halves. So the function's not defined there, but neither is its derivative. But they didn't ask us that, so I shouldn't have. Okay. But that's where, that is the derivative of that. Let's see how they did it. That's exactly what they wound up with. Now again, I think somewhere they said they like for you to write positive exponents. So get back to that. Where was that? That was a table we had somewhere, wasn't it? That we kind of glossed over. Oh, but I'm not going back and find that. Okay. Any questions on example 6? All right. If not, let's move to next topic. Simplifying derivatives. Oh, we don't like to do that, do we? Okay. The next 3 examples demonstrate techniques for simplifying the raw derivatives functions involving products, quotients, and composites. I think we've been doing this, haven't we? But maybe these are a little more esoteric. So let's do one. Here's example 7. Find derivative of that. Okay. What's the first thing you would do? Anybody?
You may
Rewrite it. That'll be what? X squared. 1 minus x squared to the 1/2 power. All right. Now, looking ahead a little bit, what are you going to have to do to take that derivative? You will have to use a chain rule, but before that, really a product rule, because you got a product there, and one piece of that is going to require a chain rule. So you're right, we're going to have to do both of those. So let's do f prime of x. How would it start? At least in product rule form. Second?
2x.
Okay, you're going to start with taking the derivative of the first one. That's perfectly fine. 2x times what? No, not yet. Remember the product rule, derivative of one times the other plus the other times the derivative of the one. Okay, so only take one derivative at a time. You took a derivative here, so that would be times 1 minus x squared to the 1/2. Leave that one alone, right? Then what? Plus x squared times. Now you got a chain rule. Okay, say that one more time. Okay, he's doing the inner part first. It doesn't matter what order. So negative, okay, sort of disagree with what you, wait. I thought that's what you were doing, but I don't think it is. Was that what you're doing, the derivative of the inner part?
No, I was already doing the chain.
Oh, wait, okay, let me erase. I was trying to follow what you were doing. You're jumping ahead. Okay, you're making that the minus. Get out of there. Okay. All right. You're doing that as a minus. Now you want to explain to us where you got that.
Well, I was already had the chain rule.
All right. Already doing the chain rule. See, normally it would be a plus, this times the derivative of that, but the derivative of that is going to come with a minus 2x. That's what I thought you were doing. That's where your minus came from, right? So that's skipping a few steps and combining them. So let's, this isn't directed at anyone, but remember KISS? Y'all don't know KISS, do you? Oh, you do. Okay. Keep it simple. We'll leave it there. Okay. So it'll be x squared times derivative of this. And what is the derivative of that? 1/2. Continue. 1 minus x squared to the negative 1/2 times negative 2x. Yes. Okay. That's that. Okay. Except we got some cleaning up to do. The first part is sort of okay. 2x times 1 minus x squared to the 1/2 plus, now, I'm going to go back to Dawson's suggestion of making it a minus, okay? Because you have a plus here, but a minus there. That's going to turn out being a minus. And let's do the numerator part first. You got a 2 in the numerator, and you got an x squared and an x. That'll be x cubed. In your denominator, you have a 2, which is going to wipe out that 2. I could have done it right up here if I'd have been paying attention. Doesn't matter. Okay, and what else is in the denominator? Help me? 1 minus x squared to the 1/2. Okay. Now, I don't know if y'all prefer radicals or the exponential form here. Might be a little easier to see talking in terms of radicals. I don't know. You tell me. This would be 2x, if we write it as a radical, the square root of 1 minus x squared, minus x cubed over the square root of 1 minus x squared. Now that's a perfectly correct first derivative. If, however, you don't like having one is a radical and one not a radical, you could put them on over least common denominator, because this is a subtraction problem, right? And how would you do that? This has a denominator of 1. So in order to get it over the same denominator, we'd have to multiply the denominator by the square root of 1 minus x squared. But if we did that, we'd have to multiply the numerator by that 2, which basically loses the radical. Does everybody see what I'm doing? Okay. So what we have now is 2x times 1 minus x squared minus x cubed over the square root of 1 minus x squared, which will be 2x minus 2x cubed minus x cubed over the square root of 1 minus x squared. I love this problem, don't you? All right. This will be 2x minus 3x cubed over the square root of 1 minus x squared. Do you see that? This may be the simplest way to write that. It's a lot more concise than this way, which I said was perfectly legitimate. But you have your denominator here and the same expression in the numerator. So if you put this over that denominator, that becomes 1 minus x squared. Then when you multiply through here, let's see if that's, well, let's see, which is this example 7. Oh, okay. Hard to keep up with what they're doing here. They do one more step, and I don't know that it's any better or worse. X times 2 minus 3x squared over the square root of 1 minus x squared. I don't see that that's any simpler, but it certainly is another form. And that's why I really don't care too much for WebAssign, because they're going to be looking for one of these 3 or 4 forms, and you're not really sure which one they're looking for, okay? So my guess they'd be looking for the last one. I see no advantage of that over the one before it, okay? But whatever floats your boat. So let's watch how they do it. Can I erase this now? Whatever you do, don't try to eat the whole elephant at once, like Dawson was doing. Okay, take it one bite at a time. Make sure you understand every step. After a while, yes, if you can skip a few steps, by all means, knock yourself out. As long as you do them all correctly. I don't want any wrong answers, okay? I don't like them. All right, so what we're going to do here, write it down again. Good. Then, rewrite it. And fractional and exponential notation. I hate trying to take derivatives of radicals, but I don't mind exponents. That's much better. This then sets up the product rule, okay? And what they did was the same thing Devin did. It'd take the first times the derivative of the second. They wrote it out this way, though. Oh, wait, I guess you did the derivative first. Okay, we'll get to that. They do that second. They do first times the derivative of the second, and it doesn't matter which order you do, plus the second times the derivative of the first. That's what you did first, okay? And when you do the derivative of this one, that's when the chain rule comes into play, okay? So it's x squared times 1/2, 1 minus x squared to the minus 1/2, chain rule times a negative 2x. That's where Dawson got his minus sign. Plus the second, square root of, well, 1 minus x squared to the 1/2 times 2x. Okay? Now, they immediately solve the 2's and the denominator 2 and the numerator divide out, bringing the minus sign out here in front, and you have minus from here, x cubed from the combination of those two, times this to the minus 1/2, and then this will be 2x times that. They just flip the order. Doesn't really matter. Okay? But that still is a little, I don't know, to me, hard to do. That would be a perfectly correct answer. Okay? But they're going to simplify it some, and boy, look at them. They're keeping it, oh my word. All right, what they're doing here, I don't think I would ever have thought of doing this. They're factoring out, you see, they got basically 2 terms here. They're factoring out an x out of both terms and this out of both terms. Yeah. 1 minus x squared to the minus 1/2 out of this term just leaves you, okay, that can come out. So what you're left here is a minus x squared, okay, when you take those 2 out here. That's pretty simple. And they put a times 1, which I'm so happy they put in there. Okay, I don't know why, but they did. Plus, and then when you take the x out here, that leaves a 2. And when you pull this out of that, okay, you're dividing it out is what you're doing. So it's this minus that, minus a minus, which gives you a plus, so that gives you that to the positive 1. I never would have expressed it this way, or tried to show it this way. That, to me, has so many places you can make a little wrong choice and get it totally screwed up, okay? So anyway, they did that. Don't ask me why, okay? Now this is out front. This you can now distribute the 2 inside that, and you can also, we did the same thing, only not this way. Minus x squared plus 2 minus 2x squared, okay? So that gives you X is up here, this goes downstairs, and then you have, yeah, this is here, and then you have 2 minus 3x squared there. Yeah. Now, do they distribute that? No, they don't. That's amazing. They would leave that, well, I guess that's fine. Yeah, we already saw they did that. They factored out the x, and that's why. Okay. If you like this way, it's correct. By all means, go with it. That is something I never would have suggested that you do, but it does work. So ultimately, you got to put it down there anyway. If you don't like doing common denominators, it may be better for you. I don't know. All right, that was example 7. How are we doing?
6 minutes.
Ooh, getting close, isn't it? Okay. Do we have time for example 8? Say again? I can't hear.
We should stop right here.
Stop right here? You're kidding me. And me rob you of a minute of your tuition $1? Oh, heaven forbid. Well, I guess I can make plenty of homework assignments instead. That would work, wouldn't it? All right, let me see if I can find the pencil here. There were a whole passel of them up here. Here we go. We'll start next time with example 8. Okay. Okay, we'll start with example 8 next time. And homework exercises here will include any of the odds 3 through 7. They're all at Calc Chat, 3's at Calc View. Any of the odds 9 through 33. There's a whole passel and a half there. All of those odds are at calcchat.com, 9's at Calc View. And I think we can go on and do trig functions. I don't see any reason why not. So do any of the odds 35 to 53. There's another big pile there. All those are at Calc Chat, 37's at Calc View. And then they have finding a derivative using technology. You can do them without, but I'll let you do whatever you want to with those. Any of the odds 55 to 59. And let's see, we're doing slopes of tangent lines. Let's see. Oh. Maybe we shouldn't do, stop at 33, because the trig functions are coming up later. So we'll do those later. So stop at 33. You have a bunch from 2.3 to do, and you got a test you're working on, right? Okay, good. A few of you anyway. All right. We'll pick up and go from there next time. We've only got implicit differentiation to go, and then I wish we had time for related rates, but I don't think we do, so we may stop there. So after the next section is going to be another test time, so that means, folks, get your first test in if you haven't gotten it in already, okay? Good deal.